Holy hell, that's loud. I didn't put on my ear thingies. What are they called? Headphones until just now? What the hell? Ah! Okay, one second. Hey, it's Poisson Invariance, your math... wait, no, I changed it. It's Poisson Variance, your math lover gamer nonsense... Wait. Guys, I forgot it. It's Poisson Invariance... Come on. Pause, brain. It's Poisson Invariance, your VTuber math lover gamer and nonsense enjoyer. Yep, yep, I got it. It only took me a lot of tries, but I got it. Whew. How is everybody doing today? Good, good. I would hope good. Or would I hope bad? I hope not bad, but I would hope good. Preferably better than not good. Preferably not bad. Preferably good. Okay. Guys, is okay good? Is okay good? I don't know if okay is good. Pretty good? Oh, pretty good. That's what we're talking about. That's what we like. That's what we want. That's what we hope for. That's our ideal. Jesus Christ, it is so freaking hot today. Fan, get more powerful. Fan, activate swivel mode. And by swivel mode, I just mean turn, and aim directly at me and stop turning. Okay, sweet. Wow. Is my model, like, lagging out? Come on, model. Anyways. I'm sorry for being late, first off, on starting. And then after that, I took a while to actually start. Because I may or may not have been painting my nails and watching a just okay movie while waiting for them to dry. And then forgetting what I was doing. Who would want to do math on a Wednesday? Exactly. Not only on a Wednesday, on a summer Wednesday. Isn't that awesome? Isn't that what you hope for? Like, you wake up, it's summer. You know, you're away from school, you're away from all that, and you're like, I want to do mathematics. No, no, you don't. But you know what? I do. I'm the odd one out. I know it. I just don't care. You can't stop me. You can't make me not care. My chat's on the left-hand side, and so if you always see me, like, looking to the side whenever I'm talking, that's why. What color did you paint your nails? Black, obviously. Not obviously, okay. It was between black or turquoise, and just the black always looks better. Because it's harder to see how terrible I am at painting them. And if they're turquoise, then it's, like, bright, and they can be easily seen. I've done them, what I've done before is, like, all black or, like, all turquoise with, like, a single one that's pink, and that one's pretty. But I digress. So I had an actual, like, PowerPoint set up for this stream, with, like, vector spaces and stuff. Now, the problem is, I did it, and I accidentally just X'd out of it. So the problem is, I set up this PowerPoint on my MacBook. And when you set up things on a MacBook, it's really, really nice when interacting with other Apple products. My PC is Windows. So I make this whole PowerPoint, and the MacBook has a built-in LaTeX equation setting and everything. If that would be finally a good time for stream. Yes, yes. Yeah, I figure people prefer, like, I'm at the basically earliest time zone in the world. And so I think people prefer evening stuff, and so moving forward, I'm going to be doing afternoon evening stuff. I think that's the play. You thought you would paint it pink and blue with pink with blue polka dots? I mean, maybe. I wouldn't put it past me. But anyway, so I did all this stuff on a MacBook, and then unfortunately, I tried to transfer it over to an actual PowerPoint, and half of it just got deleted. And I was like, okay. So you don't get it in PowerPoint form, you get it in PDF form. That's right. You get a PDF of a PowerPoint instead of an actual PowerPoint. And it's not sized correctly. And now it is sized correctly. Whoa. Okay. Why do my eyes look so sleepy? I turn my model enough, or I turn my face enough, and my model just goes. Okay, this is too depressing. Hold on a minute. You guys get to see me scroll through my YouTube too. Here's the PowerPoint. Yeah. Okay, hold on a minute. Will I choose something more upbeat? I don't know what I want to listen to. I mean, this whole mix is fun. It's only 25 minutes, but I'll change that bridge when I come to it. Did I just immediately scuff my nail on my desk? Are you serious? Gotta hit myself. Okay. I'm sorry. Yeah. I don't know how to introduce these still. Also, is my fan registered? I have two fans blowing on me. Are either put on copyrighted music? Okay. What do you want to hear? What do you want that's copyrighted? If you send me copyrighted music, I'll play copyrighted music. This isn't on Twitch. I don't care. My time zone, I don't actually know what it is to Greenwich compared to Greenwich Mean Time. I have no idea. Put on Barbie Girl? Absolutely. Okay, give me like... There you go. Well, I'm at it. Now I'm curious. PST2. So PST is GMT -8. I guess I'm actually the last person of the day. I'm behind everyone else. The world is ahead of me. We're just gonna play this right now. Actually, we're gonna play Persona music. Everyone likes Persona. You can say you don't, but you're a liar. But without further ado, or without further stalling, because that's 90% of what streaming is just stalling. Just think about it. You can just have run times that go on and on and on. I could do a 4-hour stream, and guess what? About 10 minutes of it is real content. It's ingenious. And now my YouTube studio is giving me warnings. I'm gonna ignore that. I'm gonna ignore that warning. You're at GMT -3, so it's 2015 for you. I'm at... Yes. So you're a fake? Maybe. Yeah, it's... Ugh. The daylight savings makes times for the states a mess. It's so annoying. Hi, science. I can't believe the concept of science is here with us today. Everyone, please say your scientific prayers. Our atom, who art in... Or our electron, who art in atom. Your time is 7:16 p.m. Mine is 4:16 p.m. But for people who use military time, 16:16 p.m. Oh, make a wish. I wish that I was good at math. What is this channel about? Toasters? It's mostly me just rambling about nothing, but also sometimes about numbers. Hey, don't make those kinds of jokes. It's family friendly. Okay. No, it's... I would say it's about numbers, but that's only sometimes true. I post videos about numbers, and then I stream about games or nonsense, or sometimes numbers. Like right now. Whoa. Anyways. There's a lot of this. There's a lot of me just highly respectful research in this channel. Yeah. Don't tell anyone that I spent all of yesterday editing a video of myself out of context. That's all just stupid nonsense. Highly respectable research. Okay. So today we are talking about linear stuff. And yes, that is a tiny bit of linear algebra, but it's a little introduction to give you numbers lore. Okay, so the first number is 2. Shit, I messed it up again. So a little bit of linear stuff, and this is literally just an introduction, because that's what I like to do in these. I don't like to get super in-depth with specific. What I like to do is give people a little introduction into different topics and subjects, because if you aren't big into math, like half the people in my Discord are like comp sci majors, I'm pretty sure. You know a bit, but you don't necessarily know a bunch of theory. It's finally starting, and that's my signal to delay. Are they gone? Hi, Callis, welcome. But today we are going to be talking about spaces, maps, and functions, and I'd say much more, but not much more. With me, your host, Poisson invariance. So, as I said, because I had to turn it into a PDF instead of a PowerPoint, because Keynote is Keynote. I'll stop aggravating everyone. If you are new here, then allow me to introduce myself. My signature catchphrase is hey hey. And my name is Poisson. And there's me. You can't see my mouse. Why can't you see my mouse? That's gonna become annoying. 1 minute. Capture cursor. It should be on capture cursor. Oh, there you go. Now you can see my mouse. That's me. You can see my green highlight from where I did the transparent capture. I don't have my back hair on. I don't know why. I'm a mathematician, mainly. I have a bachelor's in mathematics. I love math. I study math in my free time. I'm going into grad school for math next year. Anyways, I'm also a VTuber. You can probably guess that because I'm talking to you with an anime avatar. Most people don't look like this, I don't think. I think it would take a lot of plastic surgery, but that's just me. I'm also a gamer, as previously mentioned. That's what I like to do. That's about it. Also kind of androgynous, you can tell from the voice. I don't like to watch movies or TV shows, so if you talk to me about movies or TV shows that you've seen, you probably won't be able to get a response out of me because I don't really know any. I did a bachelor's in, yeah, it was all BS in math. The math was all BS, but it was a BS in math. I'm also an insomniac, although that is getting better with better eating, sleeping, exercise habits. Bachelor's. I'm also anemic, so I will just, like, at random times, so please. I also couldn't think of another bullet point. So that's another bullet point. Although, funny enough about the, like, doesn't watch movies or shows or anything, I did watch a movie earlier today while I was waiting for my nails to, dry. And it was almost good. It's on Netflix, and it came out, like, 12 years ago. Passage of time is weird. As I've been getting older, the passage of time is getting more and more difficult for my brain to handle. Anyways, so what's my favorite movie? Oh, my favorite movie, easy. End of Evangelion. Most people hear that that's an anime movie and just be like, okay, but what's your actual favorite movie? Like a real movie? And I'm like, actually, it is a real movie. But really, I'm just a loser. But anyways, so I watched Now You See Me, and it was almost great. It was almost really fun. Like, or no, that's not right. It was really fun until the final twist at the end was the stupidest thing in the world. And I'm like, okay, that's a twist that's literally just there so you can be like, we had a twist in our movie. Which was really annoying because it detracts from it. The thing about it is I can talk about this stuff pretty well. And then... So I can talk about this stuff pretty well, like movies and TV shows, because my brother has a degree in, literally, in filmmaking. And so he'll, like, ramble to me about different sort of things that are, like, movie-related and whatnot. And he'll be like, hey, so this movie and this movie and this movie. And I can perform analysis on things that I watch. I just don't care to. Anime, weeb, I know, right? Imagine liking anime. I actually haven't watched anime in a long time. Home poor, sir, teach beautiful math. I take offense to that. No, but anyways, thank you for prodding me to continue. I constantly need to be prodded to continue, otherwise I'll, like, forget what I'm talking about. Why do you look so stupid in that photo? Because that's a photo of me in real life. It's just brain dead. Anyway, so I didn't have a final bullet point, but that's a bullet point. Anyway, so back to my previous math stream. We're gonna have a little bit of background knowledge, and that would be in metric spaces inequalities. The reason I chose this is, funny enough, my first semester I took of analysis, we spent the entire semester just looking at metric spaces and inequalities, and my previous math stream ended up talking a bit about metric spaces, metric balls, and kind of closed and open sets, and how those are affected by metric balls and whatnot, and the rules of those. But the important parts to know is just, like, the basic of what a metric space is. So a metric space, imagine you have a metric. A metric is a measurement. What does a measurement mean? It's a measurement between 2 points. What does that mean? That means that any distance between 2 points will be greater than or equal to 0. And that is an unfinished bullet point. That didn't transfer properly. What this is supposed to say is that if this distance is equal to 0, that implies that x equals y. Namely, there cannot be a situation where 2 points have a positive distance and are the same point. The distance is the same backwards and forwards, and this is called a triangle inequality. It means that the distance from x to y plus y to z, it will always be greater than x to z. You can see that in terms of triangles. And the capital X is just a space containing said points, although those points are actually generally vectors, but we generally just say points because it's easier to or identify a space in terms of just a flat point than it is in terms of a bunch of vectors, because we can only see in so many dimensions. except if you're using matrices, then you can technically see in more dimensions, but you can't actually really visualize that beyond the matrix visualization, which I guess you could argue is a visualization, but I mean a graphical visualization. I have a lot of energy today, and I don't know why. Guys, I might like numbers. I might be a nerd. Don't tell anyone. Don't tell anyone. Guys, don't. Why are you telling people? Stop telling people. Anyways, so another important thing is to pay attention to. All right, so I guess this is worth noting. I'm not gonna go ahead and just what I want to say is that this is worth noting because you're going to be working in metric spaces and understanding how metric spaces end up with rules. And if you understand what the basis of the rules are, that's important. That being said, if you don't know anything about these concepts, you probably will not get a lot out of this presentation, but maybe you just want to hang out and have fun, because that's so, more power to you. Anyways, so secondary, we have the properties of inequalities. Now, these are important and, like, worth mentioning, but the thing is, they're kind of obvious. It's weird, but it's like where you kind of have to prove that something exists. You have to prove things, because technically these can't be axioms, and if anyone doesn't know, an axiom is kind of just a basis that we accept. Not a basis, base is a very specific word that we're going to get into later, but basically a rule of the universe that we accept as fact. So these are like a step above axioms. They're the most basic of proofs and kind of just properties. So, like I said, I've watched The Matrix, you'll be fine. Then you are the chosen one. I am very proud of you for having watched The Matrix. That was sold to me as like an action movie, and then I watched it and it was a really interesting psychological movie. So I got an enjoyable time out of it, but not the enjoyable time I thought I was going to get out of it. That was before I was in college and when I was willing to sit and watch movies, and then my brain got very interesting. So there are a series of pretty obvious things. And again, these actually won't pertain a lot to what we're doing today. It's just really important to have these sorts of backgrounds when you're trying to write a lot of proofs and whatnot. But there's stuff. So if you have the constants of A, B, C, and D that are all in the real numbers, technically this also works in the complex plane, but it gets a bit different in the complex plane because the positives and negatives for the complex or the imaginary part change a little bit, but not a significant amount. Anyways, so we're just gonna say the real numbers for the sake of ease. If A is less than B and B is less than C, A is less than C. Pretty obvious. If A is less than B, then A plus C is less than B plus C, and we're gonna assume that A or C in that case is greater than 0. If A is less than B and C is greater than 0, then A... Well, actually, no, that actually doesn't matter if it's greater than 0. If A is less than B, then A plus C will always be less than B plus C. Anyways, if A is less than B, C is greater than 0, then A times C is less than B times C. A is less than B, C is less than 0. The reverse is true. A times C is actually greater than B times C. I said A times C is, yeah, less times B. I don't know. I'm speaking really fast because, again, my brain is kind of just, like, going right now, and... I wonder if I should be on meds. I mean, I am on meds, but they're for different stuff. Anyways, this is basically the saying of, if something is less than something else, then the reverse is true for its negatives. Finally, if A is less than B and they're both positive, and C is less than D and they're both positive, then A times C is less than B times D. These are all, again, like I said, pretty simple, but worth mentioning. I am going through this way faster than I thought because I'm talking really fast. I only have 14 slides, and most of them are nonsense. So now we get to our main attraction, and this is a take on metric spaces. And they're linear spaces, they're also called vector spaces. As mentioned, actually, in one of my streams, when someone said, say a math fact, I was like, okay, these are actually the same thing. That's your math fact for the day. I have DHDA. I've been told I don't have ADHD, so I obviously must have a disorder that is hyperactive, that causes deficiency in attention. It's very different. It's very, very different. I promise you, it's very different. It's not the same at all. You're 14? What? No, I am in my 20s. Anyways, so Linear and vector spaces. They're, in fact, the same thing. What they are is a type of metric space. But a metric space is pretty simple. A metric space just has what I said earlier. It has a bunch of points. It has stuff in it. That's the summary. A metric space is a place with stuff in it that you can measure the space between the stuff. This distance to that distance, and all the stuff inside of it. That's it. That's pretty simple. A vector space is a voice crack. A vector space is like that, but instead of just having a distance, it also has a bunch of rules with how the different points interact, namely how the different vectors interact, hence the vector in vector space, because we consider most things vectors. Well, really, you consider anything a vector because you can have like a 1x1 dimensional vector, but that doesn't matter. We just think of that as a regular number then. Anyways, so if it's a metric space with a lot more rules, we have to pay attention to how the vectors interact, and because of that, a lot more rules, it means we can actually do a lot more specific stuff with it, and that's where we get into like different proofs and whatnot, because we can get trickier with it. By applying more properties, we're able to have more fun. That's how I like to think about it. If you enjoy doing this, if you have fun messing with stuff and like proving stuff, then it's totally up your alley. Like, the perfect class for you? God, one of my favorite classes. Okay, my real favorite class was like Real Analysis 1 and 2, and they have the same professor, and I still have his textbook, and he was such an inspiration to me, and he was actually a really good like life coach too. It was definitely my favorite course. Because like the first class, there were a bunch of us because it was a required class, and then the second class it had thinned down, but it was all people from the first class, and it made me so happy because so like the first class, it was like classic like classroom lecture hall kind of style. Excuse me. And then the second semester, we got this room that was just off of a library that was meant to be sort of like a mini conference room, and our numbers had thinned down significantly. So we were... Oh, which book? Yeah, don't worry. I don't actually know if he ever officially published it, because he ended up using his own book. And he gave it to us for free. And so I can actually post it in the Discord, and it'll be accessible, because it's just a PDF that he freely gives out online. And then if we wanted an actual if we wanted an actual copy, we could literally just like hand him $20. Then he'd be like, yeah, I'll print you up one. Because that was the cost of printing it. It was so funny. It's like, was he running a grift? He was kind of an eccentric guy, and that made me really like him. I don't know, there was something about him that was just like so nice. Done the Venian and Norton's theorem. No, I have not. That's electronics? No, that's actually out of... I'm pure... Or not, I'm pure math. That's separate. I'm applied math. I am purely applied math. Only Poisson, you know, is the Poisson distribution. It's fun stuff. That's actually what I'm named after. Funny enough, I learned also the French word for fish. No idea. Did not know that. Dude's last name was Fish. But there's also actually the Poisson equation. Right here. This dude right here. That guy. God, what I wouldn't give to look like that. That's the ideal male body right there. No, but it's actually a play you have like on Laplace operators and whatnot, and differential equation. Anyways, it's interesting. I don't know enough about it, and I really wish I knew more about it, because I've done like a little bit of research, but I haven't actually worked with it. There's a lot of stuff like that. In the same way that I have with like Poisson distributions a whole bunch, but the cool thing about Poisson distributions, and the reason that I named myself after a Poisson distribution, was specifically because, okay, actually the invariance, okay, one thing at a time. I keep saying okay, and then pausing, and then move to the next thing. Okay, so back to what I was saying before. The reason I named myself after a Poisson distribution is because noise. I have a background in image processing. It's something I really enjoy, and specifically, the noise in an image. Most noise we think of as Gaussian noise, because as you add enough noise, it just becomes a normal distribution. Gaussian is normal distribution, same difference. But if you reduce the noise to, I believe it's called like shot noise, what happens is it stops being a Gaussian distribution and starts being a Poisson distribution. You have a CS undergrad too? No, actually. Well, so no, I was required to do a bit of CS, and then I did an internship that lasted 2 years and resulted in me getting a publication. And that internship heavily revolved around biological image processing. And so that's, and well, I also took a graduate level course from that same professor who gave me the $20 textbook for free. That same professor invited me to his graduate level image processing course that he was starting, and so I got to do that and then do the internship and whatnot. It was awesome. I kind of miss college. It's fine, I'm going back for my master's. What is real analysis? The other term for it is geometric analysis. It basically covers a little bit of everything. It covers spaces, it covers stuff that you see in like linear algebra, matrices, derivatives, all of that. Like I said, if you want to, I'm not trying to plug. This is this is gonna sound like a plug, but I promise this is not a plug. If you want to join the Discord, I will, after this stream or later in the stream or sometime today, I will go ahead and post the textbook. But even if, you know, there's a different textbook called Spaces by Lindstrom that is a really, really, really good introduction to real analysis. And it is a really strong basis for understanding that a lot of stuff like optimization, differential equations, physics, engineering, all of those build heavily off of the concepts that you get from real analysis. So even if you're a physicist, even if you're an engineer, even if you're a data analyst, it's generally things that will be built upon that are still useful for you. What was I talking about? Oh, my name. Yeah, Poisson. Anyways, so shot noise, image processing, Poisson distribution from that. And then the other thing was that I'm pretty sure the Poisson equation is rotationally invariant, hence invariance. I also want to do stuff relating to noise later on. Maybe you've seen that one video on YouTube of Perlin noise for mountain generation. I wished one to use it to generate realistic-ish mountains. I have not. That sounds cool, though. I am always down to learn more. I like learning. Learning is fun. More people should be willing to learn. That's one of like my main reasons for becoming a VTuber to begin with, is the fact that I realized that so many people are like so resistant to learning. And specifically, it was like a video of like Gargura, I'm pretty sure, where she was like 6 times, or it was like 6 times 6, and she was like 48 or something. And I'm just like, ma'am, you're an adult. And I don't know if that was for the bit or if that was real. And both seemed problematic to me, because if it's for the bit, it means that so many people have to resonate with the fact that their highest level of education is multiplication tables. And if it's not for the bit, that's an adult woman who literally can't do basic multiplication, which is a problem in and of itself. Don't get me wrong, I love Gargura, I love Saba. She is awesome. But it was just like a trend I saw over and over and over, and I was like, guys, we need to fix this. Like, a Gargura is the whole reason I started watching VTubers to begin with. Anyways. What was I talking about? I have no idea what I was talking about. Talking about Poisson equation, rotationally invariant, my name. Also, did I just hear that Gargura shark is 48 years old? I said adult woman, but, I mean, she could be. If she is, I want to know how she does that voice, because that's impressive. I mean, some people are just, like, built like that. Yeah, I was talking about my name. How much math is needed for VLSI? What's VLSI? I don't know that acronym. The Virgin Atlantic Space Endeavor. I don't know. Where am I? But yeah, so my name, it just kind of comes out of that, where it's like Poisson equation, rotationally invariant. And then the name Poisson just seemed to fit because it sounds kind of like poison. Spooky, I know. and one of my colors is, because I had the model before, well, okay, I say I had the model, but this isn't my model. It's the free model that I change the colors on. Electronics chip manufacturing, how much math is needed for that? I honestly don't know, but I feel like it would depend on where exactly you are in said manufacturing process. Like, I feel like if you're on the assembly line for that, you probably wouldn't need a whole lot. If you're on the actual, like, design team, you probably... So what I've found is that most, so, like, physics tends to need a lot of trigonometry, whereas engineering seems to tend to want a lot of differential equations. And it's true that differential equations has a lot of trigonometry, but it seems like you get a lot... No, I guess you also get a lot more diff Q in physics. Really depends. But there's a ton of engineering problems that are just, like, heavy in differential equations. Yeah. And physics, too, because I'm just thinking about, like, the most basic physics equation we think of is also the one that we use as an example for derivatives. Guess what? Derivatives, differential equations, they're kind of related. And it's, like, you know, the position, velocity, acceleration derivative of one derivative of the other, the derivative of the other. Is the anti-position or the anti-derivative of position time? That's like a legitimate question. I saw that as a meme once, and I'm just like, I actually don't know. It's really interesting. Really interesting question. But yeah. It's like how with comp sci, the main thing you need is linear algebra. That's why a bunch of colleges won't actually teach one linear algebra course. They'll teach two different linear algebra courses. What they'll do is they'll teach a comp sci based one that's mainly applied, about the matrix operations, the matrix behaviors, and whatnot. And then finally, the more theory based one will be the one that is given to mathematicians. How much math do you know? If you had any of your fields, topics, what would they be? Okay, so, hence, as I have the degree in math, I have dabbled in a lot and done a lot. So, I know linear algebra, I know all calculus, I know discrete, I know probability and stats. Admittedly, I'm not super strong on stats because stats in and of itself is kind of its own field. I do read a lot of stats books. I have multiple textbooks that I've kind of been going over and reviewing and use a lot of stats textbooks. And hi, SDX, use a lot of stats textbooks and work and distributions and whatnot and sort of things and probability inside of processing and whatnot. So in that way, a BS in applied math is kind of like a jack of all trades of mathematics. And then I ended up pushing my specialty into specifically signal processing, which again also has a lot to do with distributions and whatnot, but then there's a lot of analysis that comes into it. And so like I've done work on a lot of, how would I describe it? Linear algebra based analysis of images, I would say. You use a lot of, and you actually use a fair amount of linear algebra in statistics. You can, because stuff like, for example, the eigen values, like a leading eigenvalue tells you the sort of most prominent direction that a data set tends towards. And so that's a, like, you break it down with SVD, singular value decomposition and whatnot, and then from there you get to then perform more analysis. In linear algebra, you only got to diagonalization, eigenvalues and vectors, Cayley-Hamilton's theorem, etc. I don't know if it's plenty for comp sci. For comp sci, the main thing is going to be, if you know what an eigenvalue represents, that's good. If you know how to do matrix operations, I can speak, matrix operations, then you're good. SVD, great one. QR decomposition, another really useful one. Grand-Schmidt theorem, that sort of thing, isn't as useful, but it's really useful on the proof side if you want to do something like prove SVD or use it to prove a QR decomposition, whatnot. So you should be good. Like, oh, the other thing I've taken is like abstract algebra. Abstract algebra is really cool. Like that's I'm so sad. GTNH. What's GTNH? Greg Tech? Ooh, what's that? What's that? What's that? I don't know what that is. That sounds really cool. I like acronyms. We were using acronyms earlier. What was the one that you said earlier? A science. Science said earlier, and I don't remember what the acronym was. Signal distribute is niche. Please tell you more about it. I don't know how to say, like, tell more about it. Like, leet code problems. Isn't leet the one where it's like, I'm thinking of leet speak. Leet code. What's leet code? Anyway, sorry, we'll get back to that. It's hard, I think, to just, like, explain, because there's a lot of different cool things to it, and it has so many different things. And that's why you get people who will write a thesis. And, okay, this is going to be outside the thing about just, like, topics in general when it comes to STEM. Or really anything, actually. The reason you get a thesis, I don't write a my microphone was speaking, sorry about that. You're not going to write a thesis on the entire thing of signal processing or anything, or image processing. You're going to write a thesis on specifically gray level co-occurrence matrices and how they behave to certain types of matrices in signal processing. That's the tough part, is it's not a specific thing. So say just like, hey, tell me more about it. Kinda tough. The easiest way is textbooks. I have a huge list of textbooks from that graduate level course I took. Some are really cool, like Verscheinen's high dimensional probability book is really interesting, and that's really applicable to any sort of analysis, and that's also really applicable to any signal processing, because a big part of signal processing is feature extraction in a similar way that is to like machine learning. There's a pretty good crossover there, and a big part of that is stuff like differential equations and statistics and probability. Anyway, so the crossover there is really useful because feature extraction, and you get features that are like, thousands of dimensions long. Sometimes some of those dimensions can be kind of redundant, so it actually does help to reduce the level of dimensionality in terms, but then you have an issue with dimensionality reduction, especially when it comes to figuring out what information you want to drop, because a big thing is that you don't know what information you want to drop, and so that's why stuff like PCA are kind of black box methods, because they're choosing what information to drop, and the same reason I don't like PCA is the same reason I don't stuff like deep learning algorithms. Anyways. Where am I? So fun fact for anyone who's new. I am never this hyper. I am only ever this hyper in math streams, and that's how I know I freaking love math. Anyone who's ever been here, like if Shane is still here, he's probably gonna be like, why are you so hyper? Because I am not this hyper when I play games. Like, at all. I am going. My brain is just on fire right now. I love it. Deep breath, deep breath, deep breath. Okay. Whew. But yes, in summary, if you are interested in more signal processing textbooks and whatnot, I can recommend you some for sure. Which part of math do you super local to it right now? I feel like I want to do a ton of stuff, like make a lot of projects, but I either don't end up having the time or skills to compete, and they feel, do they have similar experiences? Oh, yes, absolutely. I do have similar experiences to that physics guy. So, a big thing that happened to me, God, so like even this thing up here, it says image verse. That was a project I started for constructing my own kind of like machine learning algorithm, but it's really hard, and I'll get to the leak code question in a moment. Sorry, leak code problem question in a moment. 1 second. So it is really hard to focus down on something. So the thing is, you have to also understand that you will You will not make the next cutting edge machine learning algorithm on your own in your room working on a computer. You will not make the next cutting edge comp sci algorithm on your own. Okay, unless you're Vettel, but Vettel has other people working with him. Anyways, but that doesn't matter, because even if you make a project and all the project does is teach you how to do stuff, that's good. Because it's better to just sit there and figure out how someone else did a solution to a problem that's already been solved than try and figure out the solution to a problem that's never been solved. Because just the fact that you figured out the solution to the problem that's already been solved means you could have figured it out a different way. You know, everybody was going to the, like everybody, say I was trying to get from point A to point B, and everybody was like, okay, the fastest way to do that is to make 3 right turns. And you're like, what if we make a left turn? And no one ever thought of that. And the only way you did that is because first you made 3 right turns, and then you said, wait a minute, I saw that street before. I could have just made a left turn back there. But you only knew that because you made the 4 right turns that everybody else made. 3 right turns? Whatever. That's the important part. And that's the whole reason that, like, education is important. Because, sure, I could just read a bunch of textbooks on my own and never go to school. But the fact that I went and listened to a bunch of professors and interacted with a bunch of super intelligent people who said, this is how you do stuff, it made me think, oh, this is how you do stuff. What if I did stuff a different way? That only ever happens once you first look at the things that other people have done. No one has just good ideas. What's wrong with left turns? Nothing. The fact is the left turn was easier. No one has good ideas on their own without seeing everyone else's good ideas first. Like, the whole reason gravity exists is because the guy, you know, thank the apple for gravity. Now, to wind back a second. Leak code. Leak code uses a ton of algorithms which can dabble into stuff like combinatorics, but it's not math specific, it's just math heavy the more advanced you get. And after leak code is competitive programming, like in code forces, if you're a big boy programming. Yeah, admittedly, as much coding as I work with, I don't know a lot of in-depth programming. I know enough so like it's applied math, and I have a computational, my degree is technically in applied computational mathematics, so I do have a fair level of Python and R and MATLAB and C, C++ and all that under my belt, and I use all that. But I use it for the application, not necessarily for the more technical side of it, I guess. Even though I really like to understand the technical side of it, it's like I'll never necessarily learn how to program a game, but I could learn how to program a machine learning model, I guess. If that accurately conveys what I'm talking about. You need competition to grow, you guess? I would say yeah. You mentioned this guy getting the Not even there. There's many newbie level projects that you can get into. Comp-sci really feels like a Pandora's box because there's application. The more you learn, the more you can express it. Yeah. That's why if you have a problem, that somebody else has already solved, but you want to solve it in your own way with your own language, or your own code, or your own whatever, it's worth solving. Just go ahead and do it. And the reward is the fact that you did it. And sometimes that can be tough because sometimes people really do need external validation. It really depends on the person. It depends on the type of way you feel love and whatnot. For example, I am not proficient in video editing at all, but I find video editing fun. And so when I finished editing a video, I felt really, really good. And the fact that I finished editing that video and posted it, and, you know, a few people watched it, that made my day. Made my night. I posted in the evening. Regardless. But, yeah, it was really nice. And that sort of feeling is really beneficial. Hi, Aurora. Long time no see. That's not true. I saw you recently, but long time no see. Do I think CS is boring? No, I actually find programming and whatnot and coding really fun. The thing is, it's tough because, again, it's not my major, or it wasn't my major. So even if I understand chunks of it and can work in it, won't necessarily I won't necessarily be able to do the higher level stuff in it. You should try and make a machine learning project for number recognition. It should be up your alley. Just Python can be considered math heavy. That's true. And most of my work I have done in Python. Like I said, I have a published research paper. All the code in that Python. But yeah, machine learning project. Yeah, I thought about it. And I really should just bite the bullet on the amount of work it takes and just go ahead and do it. My mic is actually currently sitting on an intermediate Python coding book, and then I picked up this really cool book on the mathematics behind deep learning recently that I haven't gotten around to reading because I'm still working through this other book on Bayesian statistics that's really, really interesting because it's really simple but it's really fun. But I like the really presents all the information because you don't actually need any mathematical background to understand it, which is really helpful because a lot of people can't really get into statistics without a math background. Because there is a lot of math in stats, even though stats is kind of its own little section. Like, the whole reason it's its own degree is because it needs, like, a sprinkle of math. And then that's it. Then the rest is kind of built on itself. Although so much of it is built on, like, on R specifically now. So, like, it's more valuable for you to... If you want to be a statistician, it's more valuable for you to take a stats course and then learn how to do R, and then go from there, and then, like, funnel that into sort of, like, data analysis. But you can also funnel that, like, go from a more applied math setting to funnel into data analysis, but I find it's easier if you go the stats route, but the stats route I find less enjoyable. DevOps or, like, web development. Oh, God. I've done a little bit. Like, I know some... Okay, let's realize. I learned, like, HTML, and I took, like, courses when I was in college. Literally creative side of coding. How could it be boring? Okay, but proofs are also creative. There's nothing wrong with proofs. Proofs are fun. You can't tell, but I'm doing the fingers, the pointer fingers touching together thing. I find proofs fun. The thing is, mathematics is also creative, and that sort of thing is really anything can be creative if you're willing to put your mind into it and just kind of mess with all the pieces that you have. I guess web development could be argued to be the most, like, visually creative. But wouldn't you argue that something like designing a machine learning model is also creative because you have to do a level of visualization? And with that visualization comes the fact that you have to, like, mess with a bunch of pieces, and most models are built off the fact that you visualize something. Like, even neural networks are built off what we thought a brain was behaving like. In reality, the brain was not behaving that way at all. But our initial construction of it was under the assumption that it was behaving that way. Math is fun. Okay, bro, as you say. Sorry, don't forget my other monitor. Other monitors? I have several. I have many. I have too many. I have not enough. I kind of want to get a TV up on my computer, but I feel like that would just create a problem because I would just be straining my neck the whole time, and I don't really use it for, like, playing video games, but I don't want to do that too much because that would strain my eyes as well. But hey, that's just me. Anyways. That's, like, my favorite word to say, is anyways. My God, my brain is going today. I have no idea why my brain is so just, like, juiced today. What have I eaten today? I ate a lot more vegetables than normal. Could that be it? Get back to the vector lecture. What's going on here, though? Vector spaces? Right. Yes. Finger guns. Boom. So, as I was saying, linear vector spaces are the same thing. We went over that. Metric space is it's a type of metric space with a lot more rules because it gives you a lot more space for interaction. A note going forward, anytime someone says 0, this is a note for just sort of any higher level mathematics. Anytime somebody says 0, they mean 0 vector. they'll put it as like 0, but or the 0 with a little vector symbol on top of it, but it really just means the 0 vector of whatever dimension you're talking about, and this is really important to pay attention to. But the one place it gets messy is when you get into abstract algebra, where things get a lot less specific. So in our case, it means this. Doesn't necessarily mean it always. And the other thing that's important to note is that the operation plus means a linear combination of two vectors, but it doesn't necessarily have to be addition, how we normally think of addition. It doesn't necessarily have to be like the first part added to the other first part of the other vector. It can straight up mean a vector space where one vector plus another vector is equal the multiplications of the constants that make up the vectors. It's weird, but this is an addition operator for a valid vector space. And I forget exactly how the other stuff in it is defined, but I just remember this specific vector space being weird. When I highlight this, why does it highlight plus 0, 0, 0, and 0 vector? That's weird. But when looking at a vector space, we have a whole bunch of properties. Pros like ChatGPT, give them a prompt and it'll give you all the information. Are you saying that ChatGPT is autistic? Like me? So, vtuber teaching math speaks. Compliments make me stim. So, in a vector space, assume that we have, so our vector space, or in this case, we're going to call our vector space just the capital X there. That's pretty conventional. X, Y, Z are all vectors in the vector space. We're going to say that alpha and beta are in S, which is a subset of the complex space. This is a really messy way of saying these are just regular scalars. I don't know why we define it like this or like bother to say it. Like, why don't we just say that they're in the complex space, but complex field? But I digress. We say it's in a scalar subset of a complex field. Now, things we have to pay attention to. The additive identity and the multiplicative identity. They're going to be represented by 0 and 1. These are not necessarily your conventional 0 and 1, although conventional 0 and 1 do fill these roles in the real numbers. This is also generally, like the multiplicative identity, is like the identity matrix. You know, the like identity matrix where the diagonal is all ones. That's the multiplicative identity. So you'll see it sometimes as a capital 1. You'll oftentimes see it as the I, but when you get into something that's more abstract, you won't necessarily see it as the I because we're thinking about just like a single point. We'll represent things not as an X vector, but it's just X, so it's like easier to say 1 times X or 1 plus X or whatever, where I'm talking about the identity matrix of whatever dimension we're working in. So, important pieces about a vector space. And again, I want to point out, none of this is meant to be too complex. Kikado! 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 Hi. We're talking about math. Vector spaces, to be specific, right now. So, I have some problems for you guys at the end of this, so if you're interested in doing them, stick around. So, when dealing with a vector space, the important things are, it's a new people. Yes we do. X plus Y will remain inside the vector space. X plus Y is the same as Y plus X. X plus Y plus Z is the same as X plus Y plus Z. Now, these are all things that you might take for granted because, again, the real number space that we're all used to thinking about and working in is, in fact, a vector space. It's just a one-dimensional vector space, the real numbers, with Euclidean distance as the metrics. Ooh, you're finishing your semester. How'd your exams go? How are all of your exams been? I hope things have been going well for you. I hope that means you can stream more. So then I can... Well, I can't really raid because I'm on YouTube and you're on Twitch, but... I'll show up in your stream if you stream. I'll plug you. So yeah, these are all pretty basic things. And this bottom mess, if you're unfamiliar with this notation, You're gonna have more exams, not fun, but kind of fun because studying is fun and it's rewarding when you do well. Basically, this says, yeah, this did not format super well, but we're gonna deal with it. So for all vectors in the space, there exists a vector that's also in the space that is in fact the opposite or the inverse, the additive inverse of said vector. Thinking about it in real numbers, what this really means is, go back to streams next month, yes! What this really means in regular numbers is if you have the number 5, then -5 is also in the real numbers. If you have the number 17.8, -17.8 is also in real numbers. That's what this just says. The additive negative versions of things exist in a vector space. Basically, the way I also think about it is if I have a line that... Oh, I wish I had my iPad on me. Well, I have it on me, but I can't really stream it. Or I can kind of stream it, but it's a hassle to set up. It's not too much of a hassle, but it's annoying enough where I'd have to take a break from doing exactly what I'm doing, so then it would get in the way of what I'm doing. But basically, imagine if you have an arrow going up and down, then the opposite has to be true. If the just going straight up. If the straight up vector exists in the vector space, then the straight down vector has to exist in the vector space to cancel that out. Otherwise, if that straight down vector does not exist, or that straight up vector doesn't exist, but the straight down vector exists, then by default, that is not a vector space. The other thing to mention, linear. These are kind of like our main concepts of linearity. Linearity? Linearness? Linearity? Lines. Straight. Go do physics now. Makes sense, physics guy. There's an E. Thanks for stopping by, physics guy. Thanks for stopping by, science. Woo! So there's an evil version of the vector in that vector space. Exactly. The evil version of the vector will always exist. We're studying linearization. Or just kind of like linear stuff. Which I guess technically that does fall under. But not necessarily turning things linear. Anyways. So the basic linear properties are, if you have two scalars, and say I do a scalar times a vector, that's the same as the scalars multiplying each other times the vector. In a similar note, scalar times vector plus different scalar times same vector is the same as scalar plus scalar times vector. And finally, what we said about the multiplicative identity is over here. The identity times the vector is the vector. The additive identity is also the identity times the vector is the additive identity. Namely, the 0 vector. Guys, surprise, surprise, 0 times something is 0. I know, it's a shocker, but we had to do it to him. We had to say it. We had to put it out there. Big number will not hold me in the dark. This is my constitutional right to yell about numbers. So, get all these down. You don't have to. But these are important to write in your head. Namely, if you're in a vector space, it's going to behave how you think stuff should behave. It's going to behave in the ways that we're used to. That's the reason, well, that's not the reason, but that's the reason why the intuitions behind vector space can be so useful, because it just follows rules we already know about regular numbers. So, good. Yes, good. I like doing that. I like doing those clicks. I don't know if they're registering. In my video, I do like the finger guns. I like click and do the finger guns. I would show it, but you guys can't see. My camera's not on. I don't have it in my OBS source currently. If you think I'm gonna turn it on, that's a lot of work. And by that I mean it's one drag and drop, but I don't want to do it. So, an important, very important concept of vector spaces is the span of a vector space. And if you've heard this before, then you've probably done something with linear algebra. So, we're going to throw stuff at you that is your theory. And it's all written as theory. And there are different visualizations, and I can think of algebraic visualizations, as we see here. And you could also think of visual visualizations. That's redundant. But I didn't. And that is the only reason for that. I am lazy. And I also wrote this like 2 weeks ago. You need to sleep, need to wake up at 1 a.m. in my time zone. Okay, well, have a good night, Kakato. I am so glad you stopped by. It was so great to see you, and I can't wait till you're back to streaming. Right. I can hear more of the robot voice. But, so say we have a set of vectors. K vectors. This is all this means. We have a set of K vectors that are sitting in a space. Me too. I'm so happy. I had so much fun. So we have K vectors that are just like sitting around in a space. So if those vectors... Oh, so we have K vectors in space and we have K scalars in the space. Yes, you do. You do. You need to DM each other like nerd stuff. You have a case? You... Oh, yes, 3 blue, 1 brown. Yes. I've heard about them, and that's a really good idea. I should mention them about the visualization on those vectors. Yes. I will look that up after this. So you have a bunch of vectors and the same number of scalars. A linear combination is just defined as a summation of every vector has a scalar. We don't know what those scalars are, but we just know that every vector has a corresponding scalar, and we add it all together. Those linear combinations are how we can make new vectors, because we're going to keep the same number of dimensions as the vectors are added together using classic vector addition, and then it'll just generate new vectors. That's great. That's fun. Then we have the span of those. Now, the span of those is defined as all possible linear combinations. Namely, we can choose literally any scalar from the real numbers and then slap them onto these vectors, and it's like, what's every possible thing we can make with any scalar and any vector that's in our list of vectors right here. And, I mean, I said just that. Put any real numbers in front of each vector, and that's the span, in the span. As you can imagine, it's pretty big. In terms of real numbers, which, like, if we think about something like 3 dimensions, it's literally everything, every possible number that's in the real numbers. So there are infinite things in the span because we can just keep adding more and more things. Arguably kind of messy, but hey, that's what you work with when you're in conceptual mathematics. It's the life of it. And then when you're in comp sci, you don't have to worry about that as much. But in comp sci, an important thing will be the basis. And first before the basis is the linear independence. What does linear independence mean? So imagine you have a bunch of vectors that add to 0. All your vectors, you put them together and their linear combination equals 0. They are linearly independent if, and only if, all of the scalars are 0. This means that no vectors can possibly cancel each other out. And a way to see that is right here. So if I have a vector that in my first dimension has a number, plus another vector that in my second dimension has a number, and a third vector that in my third dimension has a number, and they all add up to 0, the only way that could be possible is if A1, A2, and A3 are all equal to 0. That's because there's no number we can multiply to get this to 0 besides 0. And say A1, A2, and A3 were all 1, then I should add up to something like 3 in the top, -2 in the middle, and 3/5 in the bottom. But I don't. I get 0. Therefore, linearly independent. Basically, it means that no position of each vector can cancel out a position of a different vector. Which then, drumroll, finally brings us to one of the most important pieces. A basis. Now, a basis is if you have a bunch of linearly independent vectors that span the entire set. So, for example, this, and like these 3 are linearly independent, and say that you can make literally any linear, you can make anything in the 3-dimensional real numbers by adding these together, then they form a basis. Basically what it's saying is that I can create anything in the space by smacking together different vectors within this basis. This is why it's useful to comp sci, is the fact that all your matrices can be created by a set number of smaller a set number of vectors and a set of vectors, a basis of vectors. So then you can work with anything easily. I don't know exactly how that's applicable, because I don't necessarily have the comp sci background to say exactly how it's applicable. But I can say that the fact that I can create anything from the pieces I have would be useful if I need to generate new data, a new model, a new placement, a new coordinate, whatever. Basically, I need to generate new information that retains the size of the information from the original thing. I can do that by having a basis. If I know that I'm able to generate information from my previous information, I wonder, actually, does that have to do with graphics? Does that have to do with graphics? Oh, that's a really cool idea. Yeah, because like images are matrix, images are matrices. And so if you're in an n by m, and you have essentially a basis for the entire field of, say, RGB, that's all you're doing, is you're just reorganizing that to then generate new matrices in order to change, for example, the pixels, the textures on an image. As much, like, I do signal processing, I do image processing, but I never think about it in terms of, like, graphics. I always think about it in terms of, like, data. And that's kind of it. But I mean, even in graphics, you're working, like, different color spaces, so it is similar enough. I don't think about it in terms of, like, changing graphics. I think about it in terms of static graphics. Because it's, like when I worked in it, I was working in histopathology. And so that means that I was taking pathological images and then analyzing them. Those aren't changing. I wasn't taking, like, pathological videos. That's an idea. That could be really expensive in terms of processing power, time. It would depend on how many frames you decide to use. I have to talk to some people. I have to talk to some researchers. So that could be really cool. Just a frame-by-frame image processing analysis of the histopathological analysis of a tumor or something. But I digress. Or, I don't digress. I get distracted. That's what I do. I've thrown a lot. So I have more. I have more. But I've thrown so much that I'm like, I don't know if I want to keep going. Because next is, like, linear maps. Well, I guess linear maps aren't so bad. Yeah. Okay, yeah. Alright. Final piece. Linear maps, or linear functions. Again, same thing. I don't know why they're called different things. Well, actually, map, we think of projection. Function is something that we help think about things easier. I feel like saying mapping makes more sense in a visualization. Function makes more sense in a more regular way of saying it, I guess. More like nomenclature, because, like, we think of things functioning, we think of performing a function on something, and you wouldn't really think about something mapping to something else until you're thinking about spaces. Fair enough. And by the time you learn about maps, you have the intuition to understand function versus map without too much trouble, because you have enough handle on stuff like calculus. But that's neither here nor there. It's actually over there. It's actually kind of here too, but... Brain, where am I? I don't write scripts for these. I don't write scripts at all. I just kind of go, and whatever happens, happens. Nothing good ever happens. But yeah. So we have a linear map. All right. So if we have a function that maps from one metric space, or we're actually going to say vector space, one vector space x to another vector space y, then This is a more mathematical terminology way of putting it, where it's like, say I'm mapping from x to y, then points in xy are defined as points in the space x. We perform the function. The corresponding points are in the point y. It's exactly what you think if you've taken any amount of pre-calc or anything like that. Yeah, no, even earlier than pre-calc. Is that pre-calc? When exactly do you first learn about functions? Like, officially under the name of function? I don't know. I want to say pre-calc, but I don't think so. Is it like the 90, the 90s? Like the math 90s chain? Oh, my finger. Nail polish is getting messed up. Just did these. Sorry. Maths help you understand laws like f inverse, f of x trick, but otherwise think about functions and programming is easier. That's actually a thing I do, where if I'm writing out something, I'll write it out as an if-else statement. When writing out function, I mean, like, piecewise functions are a great example of an if-else statement. I was writing something. Algebra 1 is graph the function. You're right. Algebra courses, that's probably the first time you hear about functions as functions. That makes sense. Yeah. You'll learn how to interact and then graph the function. Okay, fair enough. Yeah, it's been a while since I graduated high school. Oh, I graduated high school 5 years ago. I'm only in my early 20s, but I already feel so old. Anyways. So, what makes a map a linear map is if it satisfies two qualities. Namely, two qualities that we get initially from our vector space. These qualities. What it says is that if I have a function, if I'm doing a function on one point x, and then a function on another point x, that's the same as saying a function on the summation of both points in x. And if I have a scalar, then a scalar times the function on x is the same as saying the function on the scalar times x. Easy ending. Easy way to finish it off. Easy. But sorry, I'm so annoyed by my fingernail right now. I have to redo that. It's so annoying because it was like scuffed at the most annoying part. I'm gonna redo that. It's fine. I need to get like professional. I need to get like a professional manicure, like nails done by professionals, because I can't do it on my own. I suck at it. My hands are. That's a thing that comes partially with the not exercising a whole lot. Anemia as another thing is that my hands are constantly shaking, and so like trying to do my nails is so difficult because I'm just like, and then it messes up like this. Oh. Anyways, so let's practice. So this part only works with viewer interaction, and I don't know if anyone wants to actually do this or cares. But oh, I know what I'll do. 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 I'm gonna go ahead and post these in my Discord so that anyone in my Discord. This Gatorade was in the fridge for hours and somehow it's already warm. Echo. But anybody who wants to can try these practice problems, and there'll be a solution key. Solution key's right there. But they go off a bit. I should post my other PowerPoint too as a PDF. I'm a genius that I only realized that weeks late. But this one you kind of need the metric space knowledge for. Basically it says, if you have a ball of arbitrary radius centered at the origin, and we know that we have a linear map, and we know what the linear map is inside of this ball, then we want to prove that we know what the linear map is for the entirety of the function. It's the scaling property for Discord is getting lecture and homework. Yes, they are. They joined it. They joined it. They knew what they were in for. They probably didn't. They saw the cat ears. They heard the voice. They thought it was more fun. It wasn't. Anyways. And the other exercise is to show that the function of a span of vectors is the same as a span of the function of vectors. This one's kind of fun. This one's also fun. I like them both. Here's the answers for both. Don't tell anyone I showed you those. But I'm not gonna dwell on those. I'm just gonna go ahead and post those because I'm not gonna be like, all right, now sit here. Sit here and go ahead and do your homework. Guys, I have a genius idea for an ASMR video, and it's just me going, do your goddamn homework! But like whispered. Chad? Can you please do your freaking homework? Okay? Are you serious? You did not solve the last lecture's homework. Your father is going to be home in 20 minutes, and if he learns that you haven't finished your homework, you are so grounded. So get up to that room and finish that goddamn homework. Anyways, I didn't have a slide after this, so here's an image. Here, this is the power of what signal processing gives you. You to do stuff like that. Look into those cold, heartless eyes. This is the joy of signal processing. They're like, what if I just took an image and destroyed it with noise? Yeah. Yeah, this is what happens. You like it? I like it. Meme template dropped. Now, the thing I want to do is we are going to open up this, and I'm smart enough to not open up my YouTube in a tab that chat can see. No, it's just VTubers, we're fine. Analog horror, actually. 3 blue, 1 brown, span. I want to see this. Ooh. Ooh, 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 ooh. You, shut up. You, get in here. You don't show people what I'm watching. Mathematics requires a small dose not of genius, but of an imaginative freedom, which in larger dose would be insanity.
In the last video, along with the ideas of vector addition and scalar multiplication, I described vector coordinates, where there's this back and forth between, for example, pairs of numbers.
Yeah, but it's a math reaction channel, so it's different.
Now, I imagine the vector coordinates were already familiar to a lot of you, but there's another kind of interesting way to think about these coordinates, which is pretty central to linear algebra. When you have a pair of numbers that's meant to describe a vector, like 3, -2, I want you to think about each coordinate as a scalar, meaning think about how each one stretches or squishes vectors. In the xy coordinate system, there are 2 very special vectors. The one pointing to the right with length 1, commonly called I hat, or the unit vector in the x direction, and the one pointing straight up with length 1, commonly called j hat, or the unit vector in the y direction.
I love that I can hear all of his mouth
think
moisture.
Of the x-coordinate of our vector as a scalar that scales I hat, stretching it by a factor of 3.
This is a really good example.
And the y-coordinate as a scalar that scales j hat, flipping it and stretching it by a factor of 2.
I really like this representation.
In this sense, the vector that these coordinates describe is the sum of 2 scaled vectors.
Ooh, I love that.
That's a surprisingly important concept, this idea of adding together 2 scaled vectors.
Ooh, 2 scaled vectors.
Those 2 vectors, I hat and j hat, have a special name, by the way. Together, they're called the basis of a coordinate system. What this means, basically, is that when you think about coordinates as scalars, the basis vectors are what those scalars actually, scale. There's also a more technical definition, but I'll get to that later. By framing our coordinate system in terms of these 2 special basis vectors, it raises a pretty interesting and subtle point. We could have chosen different basis vectors and gotten a completely reasonable new coordinate system.
What?
For example, take some vector pointing up and to the right, along with some other vector pointing down and to the right in some way. Take a moment to think about all the different vectors that you can get
Mhm.
by choosing two scalars, using each.
That was the something that we often assume is that professor I was telling you about, who I absolutely love, would refer to it as a God-given coordinate system. We have this assumption that there is a God-given coordinate system. We have this assumption that we can only use our classic x, y. And so if you see like a function that behaves a certain way, or we were using it in terms of signals actually, we see a signal that goes up and down, kind of like a normal distribution, we assume that's a normal distribution. If you shift your coordinate system, you shift your basis, really, then you can shift the entire behavior of that function. And it doesn't have to be that Gaussian anymore. You can stretch it out. And that's actually a way to interpret an image in a really cool way, in the sense that you can then look at the behavior of the image, behavior of the pixels, and behavior of the colors and whatnot. And then basically say, if I reorient this, I can identify noise within the image, and then I can pull that noise out, because the noise is scattered among this Gaussian distribution. But now that I've reoriented it, the noise ends up here. Everything else of the other sort of more general color values that are more common, say all my color, like I'm pretty sure actually if you do like a Fourier analysis, it would be like, oh, these colors show up consistently, these colors don't. So these colors that don't show up consistently, we can remove, and so you're left with you'll probably lose some colors, because like some of the colors do show up here. So you end up smoothing over here and removing a bunch of stuff over here, and then that gives you a pretty heavily denoised image. Generally, I mean, image smoothing in general, you'll lose data. That's par for the course. But by reorienting your basis, you're able to modify the amount of data you lose by reorienting your data to perform an easier analysis on.
One to scale one of the vectors, then adding together what you get. Which two-dimensional vectors can you reach by altering the choices of scalars? The answer is that you can reach every possible two-dimensional vector, and I think it's a good puzzle to contemplate why. A new pair of basis vectors like this still gives us a valid way to go back and forth between pairs of numbers and two-dimensional vectors, but the association is definitely different from the one that you get using the more standard basis of I hat and J hat. This is something I'll go into much more detail on later, describing the exact relationship between different coordinate systems. But for right now, I just want you to appreciate the fact that anytime we describe vectors numerically, it depends on an implicit choice of what basis vectors we're using. So anytime that you're scaling two vectors and adding them like this, it's called a linear combination of those two vectors.
This is a great visual representation of what I was talking about, especially with the way they're doing A, B, because the color coding, you can literally see A, B. And a lot of people, I think a lot gets lost on them. The visual, that's really important. That when I add this vector, and I get this vector, it's hard for people, like I know it was hard for me at first to understand, and I see this a lot, to understand how these two interact to get this new one. And so I find that having the numerical representation is easier. Like an algebraic representation of a linear combination is easier, because I'm not a hugely visual person. I favor equations a lot of the time. But yeah, I forget what I was going to say to finish that statement.
Where does this word linear come from? Why does this have anything to do with lines? Well, this isn't the etymology, but one way I like to think about it is that if you fix one of those scalars and let the other one change its value freely, the tip of the resulting vector draws a straight line.
I had never thought of that. That's awesome.
Now, if you let both scalars range freely and consider every possible vector that you can get, there are two things that can happen. For most pairs of vectors, you'll be able to reach every possible point in the plane, every two-dimensional vector is within your grasp. However, in the unlucky case where your
I'm sorry. Have you guys ever seen? Have you guys ever seen like Final Fantasy 14? I used to do a ton of Final Fantasy 14 raiding. If you've ever seen Final Fantasy 14 raid guides, it's just the way it moves is exactly the same. I don't know how to describe it. It's like so perfectly where it's like the boss is gonna jump here, and then the boss is gonna jump here, and then the boss is gonna jump here. The boss is gonna jump here, here, and here. In order to do that, we have the method we call the Straglo. I don't know why it's called that. Basically, you're gonna run, you start here, then run in a counterclockwise, skipping every other cardinal position until you get back to your original position. That'll help you dodge all of the AoEs with minimal movement.
every two-dimensional vector is within your grasp. However, in the unlucky case where your two original vectors happen to line up, the tip of the resulting vector is limited to just this single line passing through the origin. Actually, technically there's a third possibility too. Both your vectors could be 0, in which case you'd just be stuck at the origin. Here's some more terminology. The set of all possible vectors that you can reach with a linear combination of a given pair of vectors is called the span of those two vectors. So restating what we just saw in this lingo, the span of most pairs of 2D vectors is all vectors of 2D space, but when they line up, their span is all vectors whose tip sit on a certain line. Remember how I said that linear algebra revolves around vector addition and scalar multiplication? Well, the span of two vectors is basically a way of asking what are all the possible vectors you can reach using only these two fundamental operations, vector addition and scalar multiplication. This is a good time to talk about how people commonly think about vectors as points. It gets really crowded to think about a whole collection of vectors sitting on a line, and more crowded still to think about all two-dimensional vectors all at once, filling
Your field cited. This is what I was talking about too, where it was saying that it's hard to visualize everything, especially if you notice some of these even look like they're pointing towards the screen. As you buff up in dimensions. So
filling up
I'll
the plane.
Continue.
So when dealing with collections of vectors like this, it's common to represent each one with just a point in space. The point at the tip of that vector where, as usual, I want you thinking about that vector with its tail on the origin. That way, if you want to think about every possible vector whose tip sits on a certain line, just think about the line itself. Likewise, to think about all possible two-dimensional vectors all at once, conceptualize each one as the point where its tip sits. So in effect, what you'll be thinking about is the infinite flat sheet of two-dimensional space itself, leaving the arrows out of it. In general, if you're thinking about a vector on its own, think of it as an arrow. And if you're dealing with a collection of vectors, it's convenient to think of them all as points. So for our span example, the span of most pairs of vectors ends up being the entire infinite sheet of two-dimensional space. But if they line up, their span is just a line.
That's why really, when you get to like vector orthogonality, actually, by the look of it, when you get like orthogonal projections and whatnot, you get these relationships of vectors that will span across like one entire dimension or multiple dimensions up to a certain point. So everything will then be a subset of this like chunk of dimensions, and we'll leave certain dimensions out of it where each vector is orthogonal to each unit vector corresponding to each dimension.
The idea of span gets a lot more interesting if we start thinking about vectors in three-dimensional space. For example, if you take two vectors in 3D space that are not pointing in the same direction, what does it mean to take their span? Well, their span is the collection of all possible linear combinations of those two vectors, meaning all possible vectors you get by scaling each of the two of them in some way and then adding them together. You can kind of imagine turning two different knobs to change the two scalars defining the linear combination, adding the scaled vectors and following the tip of the resulting vector. That tip will trace out some kind of flat sheet cutting through the origin of three-dimensional space. This flat sheet is the span of the two vectors. Or more precisely, the set of all possible vectors whose tips sit on that flat sheet is the span of your two vectors. Isn't that a beautiful mental image?
Hey, that is an incredible visualization for span, and I can't believe I never thought of that. That's cool. I need to watch more 3 Blue 1 Brown. I've been recommended countless times.
So what happens if we add a third vector and consider the span of all three of those guys? A linear combination of three vectors is defined pretty much the same way as it is for two. You'll choose three different scalars, scale each of those vectors, and then add them all together. And again, the span of these vectors is the set of all possible linear combinations. Two different things could happen here. If your third vector happens to be sitting on the span of the first two, then the span doesn't change. You're sort of trapped on that same flat sheet. In other words, adding a scaled version of that third vector to the linear combination doesn't really give you access to any new vectors. But if you just randomly choose a third vector, it's almost certainly not sitting on the span of those first two. Then, since it's pointing in a separate direction, it unlocks access to every possible three-dimensional vector. One way I like to think about this is that as you scale that new third vector, it moves around that span sheet of the first two, sweeping it through all of space. Another way to think about it is that you're making full use of the three freely changing scalars that you have at your disposal to access the full 3 dimensions of space. Now, in the case where the third vector was already sitting on the span of the first two, or the case where two vectors happen to line up, we want some terminology to describe the fact that at least one of these vectors is redundant, not adding anything to our span. Whenever this happens, where you have multiple vectors and you could remove one without reducing the span,
I don't know if
the
I might
relevant
picked up when I yelled
terminology
it the first
is
time.
to say that they are linearly dependent.
Woo!
Another way of phrasing that would be to say that one of the vectors can be expressed as a linear combination of the others, since it's already in the span of the others. On the other hand,
That's a place where, again, I find it much better for, I find it much better for my brain to pick it up if it's in matrix, like row reduced, like echelon form and whatnot, because that's a clear numerical way of me saying, like, okay, these ones will be eliminated. This is all zeros, therefore, it's not giving us anything.
if each vector really does add another dimension to the span, they're said to be linearly independent. So with all of that terminology, and hopefully with some good mental images to go with it, let me leave you with a puzzle before we go. The technical definition of a basis of a space is a set of linearly independent vectors that span that space. Now, given how I described a basis earlier, and given your current understanding of the words span and linearly independent, think about why this definition would make sense. In the next video, I'll get into matrices and transforming space. See you then.
Subscribe! I can't believe I never subscribed to them. Yeah. Thank you for suggesting that, Baron. That's such a great visual representation. Well, my model's gonna freeze for a second. Uh-oh. It's a good thing when your phone says charging on hold will resume when iPhone returns to normal temperature, and I'm like, against my face, I'm like, what's the fourth book? Don't worry about it. Do you mean this one? Do you mean this one? I'm so glad that somebody finally noticed that. Don't worry about it. No, it's a movie podcast that a friend of mine made, and so I was supporting him. It was like, Alright, can you listen to all this? They only did one season. It was funny. And so I listened to that season. I hope they do another one. But it's really funny name, and I am so glad that somebody finally noticed, because it's been sitting up on my tab forever. A good feeling when the jokes pay off. I'd say it's a joke, but it was actually just kind of there, because it was there. And not at all suspicious. And blinks aren't registering. Why don't my blinks register? Register a blink. Right. I'll be honest. I mean, these math streams generally don't go for super long, because I generally do pretty short presentations for them. And I do just kind of like spend time yapping, and it always makes me fun to about just whatever. Especially when it's a bunch of math-related topics, that made me really happy. Like the second we were talking about machine learning and whatnot, I was just like really into it. Did I have anything else planned for today? Hey, you're not suspicious with your brother being a film major and the analog horror image and all? No. Listen, okay. If I just happen to want all of the inheritance, no one can stop me. Just leave that there. Let's see. But that's all I really had planned for today. I was thinking about doing some more stuff this evening. I don't know if I will. There's a chance I just, this evening, shifted over. Sometimes I just stream nonsense. I don't know. I don't know what I want to do. Because that was all the math stuff I had planned for today. And the thing is, it's really hard to set up more math stuff. Unless I'm, like, able to take time. It's something that I do have to set up. Because without it, I'm just... Yeah, like, you can't just sort of, like, ramble forever about something. Math is one of those things that you kind of need examples for, you know? But... So, I think... What was I gonna say? Yeah, I think I might call it here just for right now. I might come back later this evening and just do something, play a video game or something unscheduled. But on Friday I have something fun. On Friday I have a thank you for your lecture, by the way. I was indifferent to math through high school, and also it really helps sound like sound nature. Aww. It's the power of anime, boys. On Friday, I have a stream where I will be playing through Dark Souls 3 for the first time in a long time, in like 5 years or something. And every death, I will spin a punishment wheel, and some of that punishment wheel will be to do math problems, some of that punishment wheel to be give math facts, and then some of that punishment wheel is stuff like eat a super spicy food, or I don't know. I'm looking for more suggestions on what I should add to the wheel. But I figure, you know, I get to write a tweet entirely written by chat. I'm sure that's not dangerous. Anyways, I am glad you all enjoyed. Thank you all so much for watching. I'm glad I got to talk about math again. It always reminds me how much I absolutely love math when the moment I sit down and I start talking about it, I just go. I just go. My brain gets so hyper. Anyways, I have been Poisson Invariance, your vtuber, math lover, gamer, and nonsense enjoyer. Thank you all for watching, and I will see you either tonight or tomorrow on Friday. Definitely on Friday, though. So, bye-bye! You have no idea how long I had to hold that ending face. I had to, like, open my eye while making sure that my model didn't open its eye so that I could hit the ending screen. Anyways, bye-bye!